Okay, so for problem 19, the way I solve this is using the loop rule and the junction rule, except in this scenario it tells us that we are looking at the potential difference between A and B. Between A and B, the potential is 0. So if we're going from here to here, we have a potential of 0. If we were to continue this loop all the way around to its starting position, based on the loop rule, we also know that equals 0. So whether you're going from A to B or B to A, it equals 0. And you can even do the entire loop together to get your solution. The second piece that I'm going to add is the junction rule, which says that I total is equal to I1 plus I2. And the current is going, and let me use different colors. It's going to go down and to the right for I2. And then it's going to go down and to the opposite direction. I got those directions wrong. Okay, for I1. Okay, so the capacitance I'm solving for is this, but I'm gonna include my upper loop from A to B in order to solve this. So if we're trying to solve, and I'm gonna use a highlighter here, if we're trying to solve the difference between A and B, and we know that that's 0, I can go from A to B or B to A and know that both of those are 0. Now in this scenario, I'm going to go from B to A, and I am going to show you in the capacitor where the positive charges build up. If my current comes out of the positive side of my battery, it's going to build up on the top of each of my capacitors, and that lets me know whether my voltage drop across the capacitor is positive or negative, and you can treat it as a battery. So if I'm going from B, I'm following this yellow highlight. If I'm going from B here to A and I'm going down and to the left, then I am going to have a voltage drop through my 3 ohm resistor, and the current is I2, so I2 times 3. And then I'm going to go up through the negative side of my capacitor and out the positive side, which is a voltage gain. And for capacitors, our voltage is equal to Q over C. And so I'm going to represent the voltage through my capacitor as Q over C. So that's a voltage gain. This is a voltage drop. And that equals 0. For the other side, I have a loop going from A to B. And so when I'm going from A to B, I am going to start with a voltage gain from my 1 microfarad. So I'm going to use red to represent a positive Q over 1 microfarad. And then I'm going to go through my resistor, and my loop is in the same direction of current. So that's minus I2 times 1 ohm equals 0. Now, what we know about capacitors in series is that when this capacitor and this capacitor are along the same loop, they have the same current, and if they have the same current, they have the same charge. So I'm not going to represent the Q's as different values because I know that they are the same. And now I can just plug in one function into the other. It's a system of equations, and solve. So in this scenario, the easiest one to solve for is I2 in the equation on the right. I2 is equal to Q over 1 microfarad. I'm going to plug that into I2 over here on the left, and I get negative 3Q over 1 microfarad is equal to Q over C. I'm solving for C, and so the this should be plus Q over C equals 0, which actually means that, yes, they do equal each other. And so my 3Q over 1 microfarad is equal to Q over C. These cancel out. I need my capacitance in the numerator, And so I get C is equal to the reciprocal of the left side, which is 1/3 microfarads. And that is your answer.